The contents are as follows: principles of turbocharging, how to increase the engine's power output, mechanical supercharging and exhaust gas turbocharging, advantages of exhaust gas turbocharging, design and function of a turbocharger, additional technologies commonly used in turbocharger installations. First, principles of turbocharging. To better understand the technique of turbocharging, it is useful to be familiar with the internal combustion engine's principles of operation.
Mode of operation of a naturally aspirated engine. In order to understand how to optimize the output of an engine, we shall first consider the mode of operation of an internal combustion engine. Most passenger cars and commercial vehicles are driven today by four-stroke piston engines. In this case, one work cycle comprises 4 strokes which run during 2 turns of the crankshaft. In the animation, we show you the 4 working strokes: induction, compression, expansion, and ejection. First stroke, induction. On spark ignition engines, the air-fuel mixture is routed as a mixture into the cylinder during induction. In the case of direct injection engines, such as that shown here, fuel supply is by direct injection into the combustion chamber. On diesel engines, too, only air is inducted. The air is inducted as the result of the downward piston movement through the inlet valve, which is initially open. At the end of the induction stroke, the piston is in the lower position and the inducted air is located in the cylinder chamber. Both valves are now closed. Second stroke, compression. Continued operation of the crank forces the piston back up again, and, when doing this, compresses the air in the cylinder. Third stroke, expansion. The fuel is injected under pressure into the combustion chamber. On the petrol engine, combustion of the air-petrol mixture is initiated by the ignition spark of the spark plug. On the diesel engine, self-ignition occurs during direct fuel injection. The explosive combustion forces the piston downwards. The third stroke is the working stroke of the engine. Fourth stroke, ejection. The outlet valve opens and the upward movement of the piston ejects the exhaust gases to the outside. The working cycle is now repeated and the engine runs.
How to increase the engine's power output. This enlargement can be achieved by increasing either the volume of each individual cylinder or the number of cylinders. More air is available in a larger combustion chamber and thus more fuel can be burnt. But this results in larger and heavier engines. As far as fuel consumption and emissions are concerned, no significant advantages can be expected. The increasing speed makes the frictional and pumping losses increase exponentially and the engine efficiency drops. The combustion air is pre-compressed before being supplied to the engine. The engine aspirates the same volume of air, but due to the higher pressure, more air mass is supplied into the combustion chamber. Consequently, more fuel can be burnt, so that the engine's power output increases related to the same speed and swept volume.
Increasing efficiency. In principle, there are three options for boosting the output of an engine. Firstly, the displacement of the engine can be increased. Secondly, the speed of rotation can be increased. The third option available is what is called charging of the engine. We wish to briefly present the three principles below. Increasing the displacement. More fuel must be combusted in order to squeeze more output out of the engine. However, this is possible only if more air is simultaneously provided to the engine because atmospheric oxygen is needed for combustion. The simplest option is to increase the displacement. The engine then combusts more fuel owing to the greater available air quantity, thus increasing the output. The displacement can be increased by increasing the volume of the cylinders, as shown in the animation, or increasing the number of cylinders. In general, this leads to larger volume, heavier engines. However, no significant advantages can be achieved for consumption and pollutant emissions. Increasing the rotational speed. The second option for increasing the output of the engine is to increase the rotational speed. In this case, the number of working cycles per unit of time is increased and the engine turns faster. However, limits are reached quickly in this case because frictional and flow losses increase disproportionately in addition to the mechanical stress. This causes the efficiency of the engine to drop and consumption to increase. Charging. In the case of the first two methods for increasing the output, the engine operates as a naturally aspirated engine. This means that the air for combustion is inducted from the environment. The so-called process of charging or exhaust gas turbocharging pressurizes the air to be inducted already upstream of the combustion chamber by compression. The engine, admittedly, then inducts the same air volume, but the higher pressure causes a greater air mass and consequently more oxygen to enter the combustion chamber. This is shown in our animation by the dark blue color of the pre-compressed air. Owing to the increased oxygen content, in turn, more fuel is able to be combusted so that the output of the engine increases at the same speed and with the same displacement.
Mechanical supercharging and exhaust gas turbocharging. Mechanical supercharging.
Charging principles. Below we consider in greater detail the options for boosting the output of an engine by charging. Basically, we distinguish between two types of engine. Firstly, a mechanically charged engine, and secondly, exhaust gas turbocharged engines. Mechanical charging. On mechanically charged engines, the air is compressed by a compressor which is driven mechanically by the engine itself. However, this means that the compressor takes its drive energy from the engine. Consequently, the increase in output achieved by charging is in part consumed again by the required drive power for the compressor. The power consumption for mechanical charging is up to 15% of the engine output. Consequently, the fuel consumption is higher than on the naturally aspirated engine with the same output.
Exhaust gas turbocharging.
Turbocharging. Unlike mechanical charging, exhaust gas turbocharging does not consume the drive energy of the engine for charging, but consumes the otherwise unused energy of the exhaust gas stream. This is achieved by routing the hot exhaust gases to a turbine on whose shaft the compressor impeller is also located. The compressor inducts the ambient air and supplies it compressed to the engine. The exhaust gas turbocharged engine, or turbo engine for short, consumes less than the naturally aspirated engine, which has the same output, because an otherwise unused part of the exhaust gas energy contributes towards the output of the engine.
Advantages of exhaust gas turbocharging.
Naturally aspirated engine versus exhaust gas turbocharged engine. Engines with exhaust gas turbocharging feature a number of advantages over conventional naturally aspirated engines. For this purpose, we shall compare here the two types of engine in respect of certain important characteristics. Engine weight. With a smaller displacement and consequently smaller engine dimensions, a turbo engine achieves the same output as a larger naturally aspirated engine. The weight of the engine per kilowatt output is referred to as the power-to-weight ratio. Exhaust gas turbocharged engines feature advantages resulting from their clearly lower power-to-weight ratio. Consumption. The turbo engine consumes less by comparison with a naturally aspirated engine of the same output. This is because on the turbo engine, a part of the otherwise unused exhaust gas energy is supplied to the engine. Since a turbo engine of the same output requires only a smaller displacement, this also reduces frictional and heat losses, which in turn benefits the consumption. Output. Exhaust gas turbocharging allows an increase to maximum torque and maximum output, since the mixture throughput per working cycle is increased by charging. This increase allows either the use of a higher output engine with virtually the same dimensions as a corresponding naturally aspirated engine, or allows what is called downsizing the engine, i.e., achieving a comparable output from a smaller and more lightweight machine. Altitude behavior. The altitude behavior of a turbo engine is far better, because a naturally aspirated engine loses considerable power at high altitudes as the result of the decreasing atmospheric pressure. The turbo engine benefits from virtually constant pressure upstream of the turbine and the lower ambient pressure, since this causes turbine output to increase. A turbo engine hardly loses output at altitude. Exhaust gas emissions. Turbo engines consume less than naturally aspirated engines of the same output, and the pollutant emissions are correspondingly lower. Turbo diesel engines are able to be operated with greater excess air, thus also allowing lower pollutant operation. Noise. Turbo engines are quieter. This is firstly because they are smaller with the same output, thus also having a smaller sound-emitting area on the engine block. Furthermore, the exhaust gas turbocharger itself acts as an additional silencer. The upshot of this comparison, in brief, exhaust gas turbocharging saves money, provides performance, and is ecological.
Design and function of a turbocharger. A turbocharger consists of compressor, turbine, bearing system, control system, Compressor. Turbocharger compressors are generally centrifugal compressors consisting of three essential components: compressor wheel, diffuser, and housing. With the rotational speed of the compressor wheel, air is drawn in axially, accelerated to high velocity and then expelled in a radial direction. The diffuser is formed by the compressor backplate and a part of the volute housing, which in its turn collects the air and slows it down further before it reaches the compressor exit. The diffuser slows down the high-velocity air, largely without losses, so that both pressure and temperature rise.
Mechanical construction of an exhaust gas turbocharger. The compressors of most exhaust gas turbochargers are radial flow compressors, otherwise known as centrifugal compressors. This type of compressor consists of three main elements: the compressor impeller, the diffuser, and the volute casing. Fast rotation of the impeller axially inducts the fresh air which is to be supplied to the engine compressed and accelerates this air in the impeller to high speeds. The air is routed out of the compressor impeller radially and is routed into the diffuser. This is where the speed of the air is reduced largely loss-free. The consequence of this is that pressure and temperature rise. The diffuser is formed by the compressor rear wall and a part of the volute casing. The air is collected and the speed is further reduced as far as the compressor outlet in the volute casing. The compressor impeller is located on a common shaft with an exhaust gas turbine. The exhaust gas turbine consists of a turbine rotor and the turbine casing. In this case, the pressure of the exhaust gases is converted to kinetic energy inside the turbine casing and supplied to the turbine rotor. The turbine rotor, driven in this way, converts the kinetic energy of the exhaust gas stream into energy of rotation of the shaft, thus driving the compressor. Design and production of an exhaust gas turbocharger necessitate very good engineering. On today's exhaust gas turbochargers, temperatures of over 1000 degrees Celsius are achieved at the turbine side, and the exhaust gas turbochargers operate at tremendous speeds of rotation of up to 300,000 revolutions per minute. This means that they make stringent demands in respect of materials, manufacturing tolerances, and bearing assemblies.
Turbine. Twin-scroll or divided turbochargers have two exhaust gas inlets and two nozzles. The turbocharger turbine converts the engine exhaust gas into mechanical energy to drive the compressor. The gas, which is restricted by the turbine's flow cross-sectional area, results in a pressure and temperature drop between the inlet and outlet. This pressure drop is converted by the turbine into kinetic energy to drive the turbine wheel. This turbine wheel is attached to a shaft and air compressor wheel so that as the turbine spins, it spins the compressor wheel, thus compressing air for the engine. In the axial flow type, flow through the wheel is only in the axial direction. In radial flow turbines, gas inflow is centripetal, that is, in a radial direction from the outside in, and gas outflow in an axial direction. Up to a wheel diameter of about 160 mm, only radial flow turbines are used. From 300 mm onwards, only axial flow turbines are used. Between these two values, both variants are possible. The radial flow turbine is the most popular type for automotive applications.
In practice, the turbo is a highly efficient, complex piece of engineering, built to tolerances of thousandths of a millimeter. It comprises a turbine and compressor connected by a shaft supported on a bearing system. The turbo is driven by the waste energy from the exhaust gas. The exhaust gas enters via the turbine housing, turns the turbine, and leaves through the exhaust outlet. Exhaust gas temperatures can reach 950 degrees C, which means that special high-temperature materials are needed for the turbine wheel and housing. The speed and load of the engine determines how fast the turbine wheel spins. With the engine at idle, the turbine spins at minimal speed. As more gas passes through the turbine housing, the turbine rotates faster. At full speed, the turbine wheel can rotate at up to 240,000 RPM. The compressor wheel is connected to the turbine by a forged steel shaft and is powered by the spinning turbine. Air is drawn into the compressor housing by the compressor wheel and is compressed as the blades spin at high velocity. The shape of the housing converts the high-velocity, low-pressure airstream into a low-velocity, high-pressure airstream at the outlet. Air enters the compressor at ambient temperature, but leaves it at up to 200 degrees C.
Bearing system. The turbocharger shaft and turbine wheel assembly rotates at speeds up to 300,000 RPM. Only sleeve bearings specially designed for turbochargers can meet these high requirements at a reasonable cost. Radial bearing system. With a sleeve bearing, the shaft turns without friction on an oil film in the sleeve bearing bushing. For the turbocharger, the oil supply comes from the engine oil circuit. The bearing system is designed such that brass floating bushings, rotating at about half shaft speed, are situated between the stationary center housing and the rotating shaft. This allows these high-speed bearings to be adapted such that there is no metal contact between shaft and bearings at any of the operating points. Besides the lubricating function, the oil film in the bearing clearances also has a damping function, which contributes to the stability of the shaft and turbine wheel assembly. The one-piece bearing system is a special form of a sleeve bearing system. The shaft turns within a stationary bushing, which is oil scavenged from the outside. Axial thrust bearing system. As the gas forces acting on the compressor and turbine wheels in axial direction are of differing strengths, the shaft and turbine wheel assembly is displaced in an axial direction. The axial bearing, a sliding surface bearing with tapered lands, absorbs these forces. Two small discs fixed on the shaft serve as contact surfaces. The axial bearing is fixed in the center housing. An oil deflecting plate prevents the oil from entering the shaft sealing area.
The forged shaft linking the turbine and compressor runs in a bearing housing, lubricated by oil from the engine. The oil is fed under pressure into the bearing housing to the journal bearings and thrust system. The oil also acts as a coolant, taking away heat generated by the turbine. The journal bearings float on a film of oil between bearing and shaft and bearing and housing. The clearances for these oil films are critical. At both ends of the bearing housing are unique oil seals. Totally unlike normal engine oil seals, they're specially designed to cope with the turbo's extreme temperatures and pressures and help ensure that oil does not leak into either compressor or turbine housings.
Control system. Full boost pressure must be available at low engine speeds. This can only be achieved with a boost pressure control system on the turbine side. Control by turbine side bypass. The turbine side bypass is the simplest form of boost pressure control. With this design, more exhaust gas than required to produce the necessary boost pressure is supplied to the turbine shortly before the maximum torque is reached. Therefore, once a specific boost pressure is achieved, part of the exhaust gas flow is fed around the turbine via a bypass.
Charging pressure control. Today, the charge pressure is normally controlled as a function of the turbine output or speed of rotation. An increasing charge pressure is accompanied by increasing speed of rotation of the turbine. The turbine output or speed of rotation is dependent on the available exhaust gas for the turbine. Small turbines are used to achieve a corresponding charge pressure even at lower loads. However, this small turbine is no longer able to achieve throughput of the exhaust gas quantity at full output. A bypass of the turbine is required in order to relieve the situation. The swing valve closes off the bypass between turbine inlet and outlet. Even with only a lower amount of available exhaust gas, the turbine achieves a higher speed of rotation which continues to rise with increasing exhaust gas quantity. When the turbine reaches the speed of rotation required for maximum charge pressure, the valve starts to open. This means that the turbine's speed of rotation remains the same, and that the exhaust gas quantity not required is bypassed around the turbine.
The wastegate which opens or closes the bypass is usually operated by a spring-loaded diaphragm in response to the boost pressure. Today, electronic boost pressure control systems are increasingly used in modern passenger car diesel and petrol engines.
A small turbine will give a good response at low engine speeds. However, at higher engine speeds it can overspeed and overboost the engine. To prevent this happening, some turbos are also fitted with a wastegate to control boost pressure. As soon as the pressure reaches a preset maximum level, a valve opens, allowing the excess exhaust gas to bypass the turbine wheel and go straight out through the exhaust. In a wastegated turbo, the turbine wheel can safely be smaller, giving better engine response and yet still maintaining maximum power output.
The variable turbine geometry. The variable geometry or variable nozzle turbochargers use movable vanes to adjust the gas flow to the turbine. The vanes are placed just in front of the turbine like a set of slightly overlapping walls. Their angle is adjusted by an actuator to block or increase gas flow to the turbine. As a result, the efficiency of the turbocharger and hence that of the engine is higher than that achieved with the bypass control. At low engine speeds, the flow cross-section is reduced by closing the guide vanes. the boost pressure and hence the engine torque rise as a result of the higher pressure drop between turbine inlet and outlet. At high engine speeds, the guide vanes gradually open. The required boost pressure is achieved at a low turbine pressure ratio and the engine's fuel consumption reduced.
Variable turbine geometry. Variable turbine geometry, VTG for short, was developed in order to further increase the efficiency of the exhaust gas turbocharger and not to bypass exhaust gas energy unused around the turbine. The guide vanes, with rotary mountings between the volute casing and the turbine rotor, change the build-up behavior and thus the output of the turbine. By closing the guide vanes, the VTG simulates a small turbine able to achieve higher rotational speeds even with lower exhaust gas availability. With increasing exhaust gas availability and reaching of the speed of rotation for the maximum charge pressure, the guide vanes are opened. The turbine increases in size, through to full output, at which time the guide vanes are fully open. By comparison with bypass control, the VTG utilizes the entire exhaust gas energy so that the efficiency of the exhaust gas turbocharger and thus the engine is enhanced. This is how a positive influence is achieved on output, fuel consumption and exhaust gas emissions.
Additional technologies commonly used in turbocharger installations. Intercooler. When the pressure of the engine's intake air is increased, its temperature also increases. In addition, heat soak from the hot exhaust gases spinning the turbine will also heat the intake air. The warmer the intake air, the less dense, and the less oxygen available for the combustion event, which reduces volumetric efficiency.
In theory, a turbo is simply a hot air pump that forces more air into the engine. With more air, the engine can generate power more efficiently, improving performance, reducing fuel consumption and cutting emissions. As temperature increases, its density decreases, which reduces power. So it's usually passed through a charge air cooler or intercooler, which uses air or water to cool the hot, high pressure.
Blow-off valve. A blow-off valve is an important part to any turbocharged vehicle. These valves save our forced induction components. These valves open whenever there is enough boost pressure in the intake pipes, and vacuum from the intake manifold. When this valve opens, it releases the pressurized air in the intake piping either back to the turbo intake piping or vents it to the atmosphere. The reason this is important is because if that pressurized air is not allowed to escape once the throttle butterfly closes, then the air will apply pressure on the turb compressor wheel, putting unwanted stress on it. While this stress is very small, over time it can cause added wear to the bearings and cause the unit to fail prematurely. A blow-off valve works the same as a wastegate does, with a valve controlled by a diaphragm. The diaphragm has a spring and a vacuum port input to help open and close the valve.